Okay, I hope you are all ready, because this video is going to blow your mind, or it's going to drive you crazy, or it's going to frustrate you, or you're going to be stoked you've been watching all these videos. This may be a very complicated video. There's a lot of information in here and a lot of steps that describe the release of insulin from pancreatic beta cells. But I'm going to tell you right up front, there is nothing in this video, in this explanation, that we haven't already talked about individually. This is going to involve the polarized state of the cell, depolarization events, different types of gated channels, leakage channels, exocytosis. So all the previous videos were great primers for understanding the release of insulin from pancreatic beta cells. So let's start identifying some things in this cell. So once again, these beta cells are found within regions of the pancreas known as the islets of Langerhans. Over here on the left, we have what's known as a GLUT2 channel. This is a glucose channel that is always open, and it allows glucose to flow into the cell. Certainly, glucose will be flowing from an area of high glucose concentration in the extracellular fluid directly into the cell where there's going to be a lower glucose concentration. Between meals, there's going to be a low glucose level, low glucose concentrations in the body. As a result, there's not going to be too much glucose moving into these cells. Right after a meal, we're going to have elevated blood glucose levels, and quite a bit of glucose will move into these pancreatic beta cells. Up here in purple, we have a sodium leakage channel. And that sodium leakage channel is going to allow sodium just to leak in, continually leaking into the cell. Up here in green, we have a potassium channel. Keep in mind, as I stated from the outset, we have all sorts of channels in this cell. And this potassium leakage channel is a gated channel. And specifically, it is a ligand-gated channel. But it works a bit differently. When there is no ligand bound to this channel, and this spot right here, this black spot, is the binding site for the ligand. So when there is no ligand bound to it, the gate is open. In the previous examples we looked at with ligand-gated channels, the ligand would actually open the gate. But in this case, when the ligand is bound to it, it's going to close the gate. Since we don't see the ligand here, the gate is open. And potassium is free to leave the cell down its gradient from an area of high concentration in the cell to an area of low concentration outside of the cell. This green potassium channel is known as the Potassium ATP Ace. And it's a very unique setup. ATP is the ligand that closes this channel. Potassium ATP Ace, when potassium binds to that channel, the channel closes. Over here in blue, we have a voltage-gated calcium channel. Calcium will move through that channel only when that gate is open, and that gate's only going to open when we have a depolarization event. Lastly, we have this secretory vesicle that is holding on to a protein hormone or protein hormones known as insulin. So the secretory vesicle is storing insulin. The only way that insulin is going to leave the secretory vesicle and out of the cell is via the process of exocytosis. Specifically, calcium-induced exocytosis, just like we saw in the previous video pertaining to exocytosis in general. Okay, so let's take a closer look at this. Like I said, right after a meal, we are going to have elevated blood glucose levels. And what you can see in this image is this glucose I have in the lower left. It's a much larger concentration of glucose than we had previously. So there's going to be more glucose diffusing into the cell down its gradients. And the more glucose we have in a cell, the more opportunity it's going to have to produce ATP. Now, to be clear, we produce ATP when glucose combines with oxygen, but that's not always the case. Glucose can produce ATP anaerobically. So whether or not this happens anaerobically in the absence of oxygen or aerobically in the presence of oxygen, it's going to be the same outcome, and that's going to be the production of ATP. So the more glucose we have, the higher blood glucose concentration we have, which is immediately after meals, the more glucose we're going to have going into this pancreatic beta cell, and the more ATP is going to be produced. There's going to be a lot more ATP, which is going to cause ATP to diffuse or disperse across the cell and go bind to that potassium ATP Ace channel. And as we talked about, when ATP binds to the potassium ATP Ace channel, what is it going to do to that channel? And if you said close the channel, you are absolutely correct. Sodium is going to keep coming into the cell, but potassium can no longer leave. So with potassium leaking in, we are now have a much larger, if you notice this green potassium right here, that's much larger than I had it written or drawn in the previous images. So we now have an increased concentration of potassium within the cell. And part of that is due to something I haven't shown in this image because it would just make the image even busier than it already is. But there's going to be a sodium-potassium pump, which is going to be continually pumping potassium back into this cell. So if potassium can't leave through the potassium ATP Ace channel, we're going to be getting an increasing concentration of potassium within the cell, which means we're getting more potassium ions in the cell, more positive charge within the cell that can't leave, accompanied by this sodium, which keeps leaking into the cell. And that is going to cause the cell to depolarize, all this additional positive charge coming into the cell or being retained within the cell. That positive charge is going to activate and open that voltage-gated calcium channel. And keep in mind, the whole goal of this is to release insulin from the synaptic vesicles. And as we know, that is facilitated by calcium moving into the cell. It happens in neurons, and it happens in pancreatic beta cells. And as you might expect, that's exactly what's going to happen. Calcium is going to come into the cell, initiate the movement of the synaptic vesicle to the plasma membrane of that cell, releasing its contents, which are insulin. Insulin is now in the extracellular fluid, moving into the blood plasma, and is distributed throughout the whole body to carry out insulin-dependent glucose uptake throughout our body, throughout those cells that rely on insulin to put those GLUT4 channels in the cell membrane of those specific cells. And we outlined that in the previous video. But just to go over these steps again, during elevated glucose, glucose moves into the cell, ends up producing ATP. That ATP is going to bind to the potassium ATP Ace channel, closing the channel, inhibiting the movement of potassium out of the cell, so it's retaining potassium. Sodium keeps leaking into the cell, adding more and more positive charge, which depolarizes the cell, opens up the voltage-gated calcium channel. Calcium moves into the cell. It's going to cause calcium-induced exocytosis of insulin into the blood plasma, where it is distributed throughout the whole body. That is the release of insulin from pancreatic beta cells.